Thank you. Hello and welcome. Thank you for coming. Uh, I just want to thank Data Science London Meetup organizers first to inviting me, having me, and also my employer Vorboss for supporting me to come here and talk. Today I'm going to talk about mostly related to Deepface, facial recognition library for Python. And to sum up, we are going to unbox Deepface package, and we are going to focus on all required stages of a modern facial recognition pipeline and the adventures I had during I developed that package. Let me introduce myself first. This is Şefik. Currently, I'm a software engineer at Vorboss. We are a telecommunication company based in London, and here we are building better connection and next generation fiber for London businesses. What's more, I'm a contributor of many open source projects, and Deepface is one of them. Also, some others are chefboost. It's a core decision tree library for Python. Retinaface, I'm going to mention it. It's a face detection library for Python also. But the milestone project of me is Deepface because it's highly adopted by the open source community. Currently, it got more than 4K stars on GitHub and 500K installations on both PyPy and Conda sources. Also, I have a personal blog, my name plus the first letter of my surname, stefix.com. I chose that name because I think that seems pretty. Also, you can find me on YouTube. I mostly share here technical tutorials in both my personal blog and my YouTube channel. By the way, I appreciate if you subscribe my channel. Finally, you can find me on Twitter with my surname. Its pronunciation is Serengil, but it's easy to type when you say its name. I promise I'm going to answer all your tweets if you mention me during this talk. As I mentioned, my speech is mainly based on facial recognition, Deepface package. But before that, I wonder how many of people in this room are currently using Apple Pay or Google Pay. Please raise your hands. Almost 90%. How many of people in this room is using Face ID or facial recognition technology to unlock their iPhone? I think 50%. So the facial recognition is the center of our life today because we are currently using, for example, I'm using Apple Pay in my daily shoppings, and I'm using Face ID technology to unlock my face to make shopping. I have interesting numbers because the probability that a random person could look at your iPhone and unlock it using Face ID technology is less than 1 in 1 million with a single Android appearance. This is 1 in 50K with Touch ID technology with your fingerprint. It's very secure, it's very safe, and that's why we are currently using face recognition technology in our daily life. Before I start, I'm going to share this information. I just get it, I just learned it. Maybe I should share this information at the end of the presentation, but I like it because this fact surprised me a lot. A group of people in Ukraine using Deepface and also retinaface packages, and those two packages are being actively used to find war criminals in Ukrainian war recently. It surprised me a lot, and I'm so proud to be the creator of that library. And you can see the picture on the left side, war criminal, and they collect the social media images from Russian accounts, and in that way they can find out that war criminal. Also, that link is not mine, but the creator of that study mentioned another war criminals investigation finding cases. Again, so proud to being the creator of this library. This all based on your imaging. You can do anything with your imagination with facial recognition technology. We are mostly using pipeline term because it consists of many stages, and modern facial recognition pipeline consists of 5 common stages. And I had to study all of those stages and learn it. Thereafter, I need to implement it in Deepface, and we are going to repeat the single line of code at the end of the presentation. A modern facial recognition pipeline consists of 5 common stages. These are detection, alignment, normalization, representation, and verification. And as I mentioned, we are going to visit all of those stations one by one. Let's visit the detection stage. We need to find the facial area in a given image to detect face, and if you are familiar with computer vision or image processing studies, you most probably play with OpenCV. It's the most common package nowadays for both Python and C++. Also, DLib comes after the OpenFace, and it's very common. Those packages provide an out-of-the-box functionality to detect face. To sum up, you give an image and it detects the faces with coordinates with 4 points on that given two-dimensional image. Both OpenCV and DLib, they are very common, but the face detection models are not based on deep learning technology. Actually, DLib wraps both a face detection model for deep learning based, and one is legacy one. But these are very fast, but these are not very robust. On the other hand, the other face detection libraries, packages, and models are SSD, is the acronym of the single shot multi-box detector. MediaPipe, also Google powered package. It has it's available in both Python and JavaScript site. And for face detection, it wraps SSD model as well. And the others, MTCNN and retinaface, are deep learning based, robust face detectors. If your task requires high confidence, then you should consider to retinaface, I recommend it, or MTCNN, because they are based on deep learning models and they are very robust, but they are not very fast. That's why if your task requires high speed instead of confidence, I recommend you to use OpenCV or DLib. And all of those packages are wrapped in Deepface package. I'm going to mention it. These are the examples for those face detectors. The base image is belonging to Emily Clark, and you can see the detected faces. I'm going to mention it in the especially representation stage. We are going to use core deep learning models and deep neural networks models, expect standard size inputs. So resizing it required before we fit those detected images to deep learning models. For instance, if you resize the detected face to the target size, it's going to be deformed, and this is going to affect the accuracy score of your facial recognition model. That's why I here added some black pixels to avoid deformation. You might see it. To sum up, we detect face and we resize it with adding some black pixels to avoid deformation in detection stage. As I mentioned, retinaface is the state-of-the-art and cutting-edge facial detector model. It's very powerful, and this is the result of retinaface model. You can see its robustness. The detection performance, even in the crowd, is amazing, and it can find even the ones in the back rows. The detector also finds some facial landmarks highlighted with red points for eyes, nose, and 2 points of mouth. We are going to use that highlights in the following stage as well. To sum up, retinaface comes with high detection score, also comes with high facial landmark detection score. This is very important. And the second stage is alignment. And let's visit that station. We basically need the coordinates of eyes to align a face. And as I mentioned, both retinaface and MTCNN provide us 5 landmark points by default. These are left eye, left ear, right ear. One is nose, and one is mouth. MTCNN, for example, gives us left eye, right eye, nose, and 2 points for mouth. But we just need the coordinates of eyes to align a face, because with high school maths, we can align it with a single formula instead of aligning it a degree. And experiments show that just alignment increases the face recognition accuracy more than 1%. That score might not be seem to offer major contribution, but I'm going to mention it. We already reach 99% accuracy for facial recognition models. So you need to apply those detection and alignment steps to have higher scores. To sum up, we will rotate the image until the both eye coordinates becomes horizontal. And the third stage is normalization. This is the optional stage. Some facial recognition studies and researchers might skip this. And let's visit it. Face detectors detect faces in a rectangular area. It might store some noise, for example, background image. We don't know the color of the background. It might be anything. And we can also find many facial landmark points of a face with both D-lib and media pipe library. Those landmark points are highlighted with red points. And currently, media pipe comes with 469 facial landmark points, and almost 70 points are coming from the face oval. On the other hand, D-lib finds just 68 facial landmark points, and a few of them are coming from the face oval. If we find the face oval with those facial landmark points, then we can get rid of the all noise information for the given image. For example, when we fit the base image of Angelina Jolie, the both D-lib and media pipe extracts face oval here. But as seen, media pipe does it much more sensitive way. And the Fourth stage is representation. That's the most important point because all of those stations, detection, alignment, and normalization are optional. Even if you don't apply those detection, alignment, and normalization, you will have some score and it might be okay, but representation is a must and it's the most important station. In this station, we are currently using deep neural networks models, but you might remember that in detection, we might not use deep neural network-based models. Why deep neural network models dominate facial recognition studies in the last years? Before 10 years ago, of course, we have some legacy approaches, but nowadays, almost all facial recognition models are based on deep neural network. That's why we are going to spend more time to understand this station, and let's visit it. This is the basic structure of a basic neural network cell, just a cell, and those cells are coming together and they construct deep neural networks models. In a neural networks system, there are inputs and they are connected to some units with their weights. For instance, the both inputs are coming from, one is coming from hand palm, and the other input is coming from the outer area of the hand, and we are going to detect the fire. This means that the weight of the hand palm is greater than the outer area of the hand because we sense much more than in that way. And weights are updated during the process. This is called training or learning in deep neural networks systems. And an advanced form of neural networks are convolutional neural networks. And these custom networks dominate computer vision studies recently because basically they are very good at detecting some patterns in given data. For example, in neural networks, regular neural networks, we feed all pixels of the image to classify it's a cat or it's a dog. But in convolutional ones, we just try to detect some patterns, for example, ears or tail or mouth. In that way, we are going to decide this is a cat or this is not a cat. Its computation cost is less than the regular neural networks in that way. And how we implement, how we use convolutional neural networks in facial recognition studies. Suppose that you have a data set consisting of 100 identities in the columns, and each identity might have more than one picture. Firstly, we are going to build a neural network structure, and this given model is a VGG face, Oxford University's visual geometry group create that model. That's why it's called VGG. That model is very good at image classification tasks, but same model with different weights. It's tuned for just facial data. And as seen in the output layer on the left side, there are 100 nodes, 100 outputs. And each one is corresponding to an identity in our data set. And one for Angelina Jolie, 2 for Jennifer Aniston, and 100 for Scarlett Johansson. And how those networks are trained, when we feed the images of Angelina Jolie, we know its output should be 1. This means that the light for the Angelina Jolie should be 1, and the others ones should be 0. And we also have the input images as pixels and outputs. in that way, neural network training algorithm, most probably backpropagation algorithm, update weights of that network based on this input and output pair. Thereafter, we are going to feed the instances for the second identity in our data set. This is Jennifer Aniston, and we know that the corresponding output should be 1 and others should be 0. In that way, our neural network continues to update their weights. And we skip all instances. And the last one, Scarlett Johansson. We feed the images for Scarlett Johansson, and we know the output for Scarlett Johansson should be 1 and the other ones should be 0. And neural network continues to update its weights, and learning is done in that way. This is the regular classification task. Thereafter, when I fit the images of Scarlett Johansson, for example, except those ones, the network is going to find this is Scarlett Johansson, and its output should be close to 1, and the other outputs should be close to 0 in that case. But this is finite field problem. I mean that we have 100 identities. You can imagine that you are working for a company with 100 employees. In that way, you can train your custom model, and that model is going to predict the identity of a given image. But what if a new person is going to join to your company? Remember that we have 100 identities. What if it's going to be 101? The first approach might be adding a corresponding output node for the output, and it's become 101. And we are going to continue to train that neural network. It's a good solution. What do you think? Firstly, I wonder. It's not a good solution. Yes, you are right. This is not going to work because our model structure is changed. Our number of nodes in our output layer was 100, and now what becomes 101. Also, our model will become more complexer because the number of weights also increased. We need to retrain the model always when that's training is done, and when a new member comes, thereafter we need to retrain it, and we don't know about accuracy thereafter the new member. It might have a low accuracy score, and your facial recognition model will fail in that case. What's more, we won't have a centralized model. I mean that my company can train our facial recognition model, and other company can train their recognition model with different input instances. It's not centralized, but we want a centralized model. I mean that I'm going to build a facial recognition model, and anyone can use it. To sum up, we really need something different. By the way, do you remember that this ads? As I remember, Volkswagen's local ads. I really like it. If you haven't watched it, I strongly recommend to watch it. As an alternative, as you mentioned, adding a corresponding node for the output is not a good choice. Here, Katy Perry joined our team, and we trained our model for 100 identities, and there is no corresponding node for Katy Perry. But our training was done before, and when we feed this input image for Katy Perry, our network is going to produce an output. And for example, 0.03 for Angelina Jolie. It's a probability. You might think that's a probability. And we are going to use those probabilities, output layers probabilities, for this given image. And by the way, this is called representation in facial recognition studies, or embeddings. You might hear those terms. And we are going to use those output embeddings for our facial recognition studies. In that way, we will have a generalized model. I'm going to train my model for 100 identities, and I'm going to share that model, and anyone can use it. I can train that model for 1,000 identities, but it's going to be a general centralized model. Anyone can use that model later. We don't need to retrain the model because you remember when Katy Perry joins our team, we need to retrain it, but now it's already trained, and we are going to use that deep neural networks model as is. We've not trained it and use it always. And finally, complexity of our model always is always same. What does it mean? I always know the predict the average processing time for that network. When I feed the image, I'm going to know, for example, I'm going to have the output embeddings in a second or half second. As I mentioned, representation stage is fully based on deep neural networks models, and these are the common facial recognition models for today. The first one is VGGFace. It's built by Oxford University researchers. The second is FaceNet. It's developed by Google. OpenFace is developed by another British university, Carnegie Mellon University. Deepface is built by Facebook. DeepID is a Chinese model. As I remember, that's built by Hong Kong University. DLIP DLIP image processing library has its own facial recognition model, interestingly. And finally, SFace. At this point, there is a de facto standard for evaluating your facial recognition model's accuracy. And there's a data set, you might know it, LFW, labeled face in the wild. It stores many face pairs, and the task is labeling those pairs as same person or different person. I'm not sure, I'm not remember the number of instances, but the task is easy. And when people, a lot of people label those labeled face in the wild data set, averagely they have the accuracy of 97%, 97.53. But all of those models already reached and passed that accuracy. For example, FaceNet model has 99% accuracy, and many others already reached and passed that accuracy level of human beings. It's very important. Sorry, there was an issue in my phone. And the final stage is verification. And let's visit this stage. But before visiting that station, I like this poet. It's a poem. It's a poem of very famous Turkish poet. In verification, we are going to adopt this idea. And in that poem, it says that the longest distance is not to Africa or China or India, not to the planets or the stars that sparkle in the night. The longest distance is between two minds that don't understand each other. I hope we all understand each other. In the verification step, we are going to use the distance. You might remember from the high school maths, Euclidean distance. It has a basic formula, but we always use that formula for two-dimensional points. And if you have the coordinates of a point, x1, x2, x3, and the other point, y1, y2, y3, we are going to find the distance between those points with this formula. Because we are going to represent facial images as embeddings or vectors. Those probabilities are just vectors. And instead of 3, we are going to have many dimensions. For example, VGG face model produces 2,600 dimensional outputs. But when we feed to one face pair, that VGG face model is going to produce two different 2,000 dimensional vectors. And we are going to find the distance between the embeddings with that formula. This is not the only way to calculate the similarity or distance between 2 points. For example, cosine similarity is a common way to find the similarity, but this is easier one. That's why I mentioned this. Thereafter, we feed facial images to our deep neural networks models, and it's going to produce many vectors. Thereafter, we are going to find the distance between those vectors. When we see the examples for same person, the distance becomes, for example, 3.5, and the examples for different persons, it becomes 5. Thereafter, we can say that if the distance between a face pair is less than 4, then it's going to be same person. Otherwise, it's going to be different persons. This is the basic facial recognition task in our studies. And an example from Game of Thrones. Daily appearance of Emilia Clarke is very different than its role in Game of Thrones. But our facial recognition model finds it easily. And all possibilities are right in this example. We have mentioned the required stages for a modern facial recognition pipeline. It might be confusing, but it is a better way. It is a simple way, and it's Deepface. And it wraps all those required stages. Instead of visiting those stages, you can just use the Deepface library. It's the first Python package. It offers out of the box facial recognition and facial attribute analysis functionalities. So you don't even need to acquire in-depth knowledge about the processes behind it, and you're able to build and run facial recognition pipelines with just a single line of code. It's fully open sourced and it's licensed under MIT. It means that you are freely used to. You are able to use it freely for your commercial or individual purposes. It's also published on PyPy and Conda, and currently it's got 500K installations on those sources, and in GitHub it has more than 4K stars. As I mentioned, it's available in PyPy, and you can install that package with just that command. Pip install Deepface. Thereafter, you are able to import the package. And once you import the package, you are able to access its functionalities. And verification is just one functionality. And it expects an image path. By the way, you can pass URLs or basics for encoded images here. But the easiest way is to pass exact image paths on your file system. In that way, it's going to return an object. And this is the example. its response has 5 different keys, and you just need to focus on the verified key. For example, in this case, it returns true. This means that this face pair is same person. How the face decide this same person? The distance between this face pair is 0.32, but the threshold for the current model is 0.40. So it's less than the required threshold. By the way, current model is VGG face. If you haven't passed anything here, it's going to use VGG face and cosine distance as a to verify faces. So it's verified. It's very easy. We just fit the exact image paths for 2 person. We know that they are same person. As I mentioned, there are lots of state-of-the-art facial recognition models, and Deepface wraps all of those models in the background. Currently, there are 8 models wrapped by Deepface. I forgot to add here S-Face, for example. And there are also many facial detectors. You are able to specify them with those optional arguments. For example, here, if I haven't passed anything, it's going to use VGG face, but here I want to use FaceNet model to recognize face. And as a face detector, I'm going to use retinaface. Then after, its output will be the same. I'm going to just focus on verify key. By the way, for example, your case might be different. You might need to get the distance and threshold case in the response and compare it if you don't like this threshold. I mean that you can customize the output in that way. We always said facial recognition, but this task is verifying a face pair. It's actually verification, but the confusion comes from the research in this field, researchers in this field called this task facial recognition, but actually it's a face verification. You feed a face pair and it returns true or false. So if you have an image pair and you want to learn they are same person or they are different persons, this is going to be actually face verification in their language. And its complexity is 1. And basically, is this mark or is this Shefik the task you need to run? Because, for example, I want to log into my bank account with my face. My facial image is stored in the database of my bank. And when I want to log in, my image is taken at that moment, and it's going to compare the image in the database. So the task is, this is Shefik or this is someone else. As I mentioned, its time complexity is O1. By the way, actually, its time complexity is OD, and D is the number of the dimensions in your embedding. But we are going to focus on a big problem. That's why we can ignore the D and we can say it O1. On the other hand, face recognition is a task to find a face in a large database or data set. And its complexity is actually O, D times N, but we are going to ignore D, and its complexity, we can say ON. When we compare O1 and ON, it might not be a problem for a database consisting of 100 or 200 instances. But suppose that you need to find a war criminal in a large data set for all people, millions of people. This becomes problem. You need to compare that image with 1 billion or 10 billion instances. It's going to be problematic when N becomes bigger and bigger. But actually, face recognition task includes face verification. We need to apply face verification task n times. Luckily, Deepface can do it in the background, and you don't need to do it in a for loop. You should mention the identity you are looking for. Here is the target.jpg, and I'm going to look the identity of that image in that folder, and I'm going to store my facial data set in that folder. Thereafter, it's going to return a pandas data frame, and the most probable identities, matching identities for that given picture. For example, in this case, I put the image of Angelina Jolie, and in that folder, there are 3 different images of Angelina Jolie, and it returns this. Besides, it returns the distance, satisfied distance. In addition to its facial recognition model, Deepface comes with facial attribute analyze functionality as well, and we can fit a input image, and we can analyze its age, gender, ethnicity, and emotion. It basically analyzes the apparent age, gender. Apparent age is not the exact age, but suppose that what if I ask to this committee how old I am? Thereafter, I'm going to take the average of the responses. That's the apparent age. We have a data set for many instances predicted by many voters. In that way, I train a model to predict the apparent age. In this way, we can fight with biased data sets of training of the facial recognition models. Also, we can decrease the search space with demographic information. For example, you need to search an identity in a 1 billion identities. Thereafter, if you apply this analyze functionality first, and for example, you know its gender, you can decrease your search space to half. Thereafter, if you know its apparent age, you can decrease your search space as well. Here, age prediction model has plus minus 4 years mean absolute error. And gender prediction model has 97% accuracy and also precision and recall. So they're robust models. But as I mentioned, facial recognition is a task to search identity in a database. And what if your number of instances on your data set is very large? Suppose that 1 billion. You can think I can use the big data technologies, and that's the iconic mascot of the Hadoop. It's elephant. We can use Hadoop for that kind of big data tasks, or we can have something different. Before that, I tested this image on Google Images, and when I fit the image of Angelina Jolie, it returns some examples of Angelina Jolie and I think Monica Bellucci. But Google recognized that face, and imagine that how many images Google indexed, but it can return those images in milliseconds. It's a very challenging task. Do you think this is related to hardware Google has? I don't think so. Similarly, Facebook image tag model, you might know, it applies similar procedures when an image edit, and even if the editor is not your connection, for example, here it says that that person you have to mutual friends and edit the photo, and most probably you are in that picture. Even if the other is not your connection, but face recognition model can find you just in seconds. And imagine that how many people and how many images are indexed by Facebook. That's really challenging task, and it might not be related to the hardware Facebook has. Of course, Facebook has very strong hardware, but that might be the reason might be different. Before that, this is one of my favorite sentence, and this is a well-known Turkish photographer, Araguler, and he says that if the best camera had taken the best photo, then the one would be the best novelist who has the best typewriter or best keyboard. This is not related to hardware Google or Facebook have. This is related to approach they are applying, they are running. As I mentioned, demographic information, including age, gender, and ethnicity, can help you to decrease your search space. But it's still not enough. Google and Facebook here are running approximate nearest neighbor algorithm. You might know of KNN algorithm, K nearest neighbor, instead of KNN. And that algorithm's time complexity becomes really small when it's compared to KNN, because the time complexity of KNN is N, but here they can reach to O log N. This is very important for big data tasks. And Spotify uses that algorithm in playlist recommendation in our daily life. Currently, we have some libraries running approximate nearest neighbor algorithm, and those are Spotify and OI. That's the acronym of the approximate nearest neighbor, OYE. Facebook Face, it's the acronym of the Facebook AI, similar to search. NMS Lib, that's the acronym of the non-metric space. Also, Elasticsearch wraps NMS Lib. You are able to use it. I haven't used Milvus, but it's a competitor of those packages, and also Pinecone. Those frameworks are open sourced and run approximate nearest neighbor algorithm. What does it mean? For example, if you find embeddings of all your images, I mean that you might remember that it found the images of Angelina Jolie on the right side. All of those images, they were represented beforehand. And BGG face has 2,000 dimensions, but suppose that we have vectors for 2 dimensions. When you have an instance, for example, at this point, have a vector. If you need to apply KNN algorithm, you need to compare that point with all points in this image, and its complexity becomes ON. But approximate nearest neighbor algorithm applies a heuristic approach and decreases your search space and find similar vectors. It comes with some pros and cons. It can return the responses very fast, but it might miss some instances. For example, this vector is much similar than this vector, but this algorithm missed it. It comes with some cons, of course, but its time is amazing. So we know that both Facebook image tag module and Google reverse image search, they are applying this algorithm. By the way, you can use the Deepface to find embeddings directly. If you call represent function, it's going to return an array. For example, FaceNet model is going to return 128 dimensional vectors. And if I create this image and I use the VGG face for model, it's going to return 2000 dimensional images. And I use the color bar to represent the output vector. And we are going to discuss the recommended tech stack for both face verification and face recognition. And as you see, face recognition includes face verification. If you are going to use, if you are going to run face verification, then you might remember that its complexity is O1. And please consider the use case. We will log into a mobile application of a bank, and my facial image is already stored in the database of that bank, and that bank knows the embeddings of my facial image. When I try to log in, it takes my image at that moment, and it's going to compare with the image. It's going to be compared with the embedding, already calculated embedding. So you can store those embeddings in relational databases. But vectors are not a good type. Vectors or arrays, actually. We can say that those outputs are arrays, and arrays are not a valid data types for those relational databases. You can store the value of each dimension in a column or in a row based on your design. As a better way, I recommend you to use key-value stores. Here you can use Redis or Cassandra as a key-value store, because even though relational databases are very good at storing and collecting relational data, here we don't need a relational data. We just need an embedding of a customer, and that's the key-value store, basic key-values. In this case, relational databases cannot work as fast as key-value stores. Key-value stores are much faster if you need to access a key. Besides, you can store a vector or array in a key-value store as is. I mean that both Redis and Cassandra has a array type. You don't need to store it as columns or rows. In that way, you are going to access that embedding directly. So you don't have to expose its dimensions similar to relational databases. Notice that face verification is a subset of face recognition. So you can use the same technology and same tech stack of face verification in facial recognition as well. But when data size becomes bigger, then those are not going to work. In that case, if your task requires high confidence, I mean that you are going to search a guilty in a citizen database, you cannot miss any possibility. You should use KNN algorithm, K nearest neighbor algorithm. In that way, you are not going to miss any identities. NoSQL technologies such as Hadoop, Hive allows you to run SQL-like queries on your big data system. Spark, those are good at running KNN algorithm. But you have to spend a lot of money for the hardware to run those technologies. On the other hand, if your task requires high speed instead of the confidence, similar to Google reverse image search or Facebook image tag module, then you should I recommend to apply an approximate nearest neighbor algorithm, and those are the candidate stack for ANN algorithm: Spotify Annoy, Facebook Face, NMS Lab, Elasticsearch, Pinecone, and Milvus. To sum up, Deepface is a lightweight framework. You can use any functionality, including verification, find function for facial recognition, analyze function, find embeddings with a single line of code. You don't even need to acquire in-depth knowledge about the processes behind it. Secondly, it's easy to install and run. Some of the popular facial recognition libraries require core C and C++ dependencies that makes them hard to install and initialize. You might have some troubles in the compile step. However, Deepface is mainly based on TensorFlow and Keras frameworks, so it's very easy to install. Thirdly, Deepface currently wraps many state-of-the-art facial recognition models and face detectors. The list of the supported models and detectors has been expanding since its first commit, because in its first commit, it just wraps VGG face model. Thereafter, those models have been added. And it's going to grow over the time. Fourthly, it's licensed under MIT license. This means that you are completely free to use it for both individual or commercial purposes. It's totally free. Besides, it's fully open sourced. You can customize the library based on your own requirements. Moreover, it has a growing community. It's highly adopted by the community, and I mentioned it. Currently, it has 4K stars on GitHub and 500K installations. And what's the advantage of it? If you have a trouble, then a person in the community might have that issue, and you can find your answer on even Stack Overflow, any discussion forums. By the way, currently it has more than 20 contributors. Most of people found some bugs and fix them, also add new features. I'm not just the main creator for today. I'm currently maintaining it, but today it belongs to the community. It has more than 20 contributors. And finally, Deepface is a language independent package. I mean that it's, even though its main functionalities are based on Python, it has a API, and you are able to run those verify function, analyze function, those functions with your Node client, for example. A review of modern facial recognition pipeline has been done in Stock, and then the description of the Deepface framework has been made. I try to make facial recognition very easy and simple. We then mentioned how to use Deepface with some advanced technologies and make it highly scalable for problems. I thank you all to come here and listen to me. If you have any questions, I will be happy to answer. Thank you very much.
About you mentioned that you can use different models. Did you compare them with models and functions? Which here is best?
First, I published a research paper about that, and in my experiments, FaceNet facial recognition model and Euclidean distance, but it's L2 form. It has the most robust results. Yes.
There was like you can predict age, race, and everything. Where did you find the label things?
It's available in the repo. I don't remember it. But
it's already.
Yes, it's available. You can find out the, for example, here, if you visit the link of H, it's going to it was mentioned here. Yes. Sorry.
How easy would it be to add your own model to this API?
Very easy. Let me show you. I'm going to show the source code. Firstly, the hardest part of a model is storing its weights, and weights are not stored in the repo. I mean that you need to visit the base models folder and let's visit VGG face. You need to create your own model in that folder. Thereafter, you need to build your model structure and reference its weight file. And let me show you. Model files are stored on your environment here, but it was installed from that link. You just need to create a file in the base folders. Thereafter, it's very easy to add in a model. For example, here, S-face model is added by someone else, and he sent a PR, and I approve and merge it. Yes.
So you spoke a little bit around the hyperparameter tuning and the difference between ANN versus KNN. In terms of model performance, is obviously really good, but do you notice that certain features within the model are kind of explain more of the performance? So, for example, you mentioned with age, gender, ethnicity, you still get high performance when you're predicting all of those. But do you notice that different features explain depending on what you
We actually just use the facial image. We don't use any feature here. Images and pixels of an image is our features here. I don't mention anything else. I think that's all. Thank you again. Come here and listen to me. Thank you.